Okay, let's get going. It is my great pleasure to be able to introduce Eric Betzig to you today, who doesn't need much introduction here at Janelia, but I want to just say a few things. First, I think it's not, it's widely recognized that Eric is really one of the premier inventors in the biological as well as physical world. His work, as you're going to see here today, has really impacted biology at all levels. Not only has he won the Nobel Prize in chemistry for this work, but he's been really just tremendously impactful throughout at least the biology world that I'm familiar with. Let me just give you a little bit of background for Eric. He was an undergraduate at Caltech, and then he moved to Cornell, where as a graduate student he developed near-field microscopy, which is no small feat as a graduate student. He then went to Bell Labs, where he, interacted with W.E. Morner, really seeding the idea of single-molecule super-resolution imaging. After leaving Bell Labs for a brief stint, he then sort of dove back into his imaging world and developed Palm together with Harold. I was very fortunate to be able to watch this development because Harold and Eric actually did the original Palm experiments at NIH in my lab, and I'll just give you a quick little fun vignette. It was happening over the winter where they were developing, the original Palm microscope, and he was putting images, little slides of GFP tag proteins, photoactivated proteins that we were giving to him. And I remember one late evening coming in to the dark room, and it was absolutely freezing. It was like, it was just like going outside, doing work outside. And I said, Eric, let me get you a heater. You guys need a heater in this room. It's just way too cold. And both of them, Harold and Eric, said, oh no, we want it cold. It keeps us awake. We're doing work all night, and literally they worked all night when they were doing these experiments. So I really was very impressed. But Palm was just the start of Eric's sort of explosive innovation in the imaging realm. He then moved to doing live cell single molecule tracking. Then he moved into a whole new space, lattice light sheet microscopy, which we're going to hear all about today. Now, even though Eric has won many, many honors, I want to say, to me, what is really hilarious is my husband's just been reading Dan Brown's latest bestseller book about consciousness, and the way they get insight into consciousness is by using Palm. So it's like, connecting, when you get to a level where you're talked in these big bestseller, crazy, novels sort of exploring the nature of consciousness, et cetera. When your technology's been used for that, you've really made it. So anyway, Eric, it's a delight to have you, and let's welcome him.
Well, thank you very much, Jennifer. I'm obviously as indebted to you as I am to Harold for the Palm and everything else, and also our relationship we've had here at Janelia over the years. So, and it's always good to be back. I'm not a biologist, but I'm going to rant a lot about biology. I feel like I've learned it by osmosis, and one of the things that I feel is that biologists don't yet really fully, in their gut, appreciate how insanely complex living matter is. So people will look at simulations like this and think, hey, we kind of know what's going on. Here we got kinesin working along microtubules. It's not like that at all, okay? Not even remotely. So a very interesting paper I found when I was preparing this talk was, is the cell really a machine? Which really parrots or presages a lot of the ideas that I talk about in this talk about how crazy complex life is and how difficult is the task to understand it. So there are other simulations more recently that show a little bit more why that first one is crazy, because A, it's got a hell of a lot of empty space, and B, everything is moving deterministically like a machine. No. Everything is wiggling under Brownian motion inside of the cell. Everything is crazily densely compact. Every cell has about 42 million protein molecules of 20,000 different types. The reality is when you say lattice, light sheet, and single molecule tracking, is that the velocities of those single protein molecules is probably 100 times greater than in that simulation there. It is a crazy stochastic environment in which things are happening. It's nothing like the pictures people have in their heads of how biology happens. So the reality is that everything that we are starts from the stochastic motion of single molecules that are expressed. These start to form together in larger aggregates, and eventually in large enough systems like organelles to have basically autonomous cells that can actually reproduce. And then eventually they start working together in groups and in larger things to make our brain and so forth. And so the way I as a physicist looks at it is life represents many, many layers of emergence. And it's the diversity of the components and their interactions with one another, which, even though at the fundamental level is all random, by law of large numbers, you start to get determinism through different levels as you go through the system, all the way up to the freaking biosphere. That's where it ends, okay? So, 42 million protein molecules per cell, 37 trillion cells in each of us. So, from doing 20 years of biological imaging, we've arrived, my group, with 3 fundamental truths. Since the dynamic relationships define life, cells must be studied live, not in EM, not anything else like that, not by molecular biology, by looking at them live. To ensure that all the players seen and unseen are present, they have to be studied whole. You can't do reductionist approaches and see only a part and miss a lot of parts. Third, to observe that we're looking at physiological phenotypes, we have to look at them in the multicellular systems in which they evolve. Cells on cover slips are incredibly artificial. We know the phenotypes we see are the results of gene expression. We know gene expression is controlled by the local environment. You put a cell in the wrong environment, you're going to have the wrong phenotypes, and it doesn't matter how good your microscope is, you're going to be studying artificiality. So these are the 3 truths we hold to be self-evident, which is the basis for everything we do in the ABC at Berkeley now. And we have only one tool that can attack this. It's the optical microscope, because only it has the gentleness, resolution, speed, and sensitivity to look at subcellular dynamics. So this is not just of academic interest. So Roger Perlmutter, who's a buddy of mine, is probably one of the greatest drug discoverers in history. And what he says is most drug candidates don't even come close because we have no idea what we're doing. It's a bloody miracle if you make a drug that works. The clinical pipeline is about taking some compound that comes out of some assays that are incredibly reductionist, putting it in this black box, which is phase 1, 2, 3 clinical trials, crossing your fingers and hoping you get a result out of the other end. And that's why drugs are so expensive. That's why they're so slow to produce, okay? We need better means to understand the system and the complexity of the system. I don't know why this guy didn't turn on, but the reality is things are really complicated, okay? So the good news is that over the time that I was at Janelia, we developed a lot of tools from lattice light sheet, PALM, SIM, single molecule tracking, adaptive optics, to be able to do what we need to do, which is to look at subcellular dynamics in multicellular systems non-perturbatively. And These tools cover a ridiculously large range of space and time, which they have to because biology itself covers a ridiculously large range of space and time. So the problem is if you're going to look at living specimens with high resolution over large fields of view for long periods of time at high speed, what that means is you get crazy amounts of data, okay? So we are living in the land of crazy data. We get 4 terabytes per hour out of one of our scopes. This example on the right that was published in Science a couple weeks ago, that's one olfactory bulb, half a petabyte of data, 500 terabytes of data, taken in 10 days, okay? So we live in a world of vast data. We have spent tons of time and effort to develop both the hardware and the software tools to be able to take that data as it comes out of the scope and in real time be able to do all the deconvolutions, deskewing, compressing, and so forth to put that all together. But we're still lost. Why? Because this is what biology really is. This is a little tiny chunk of zebrafish brain tissue with 3 or 4 organelles labeled, membrane and 3 organelles. That's what it looks like. Tell me how the hell you're going to make sense of that, okay? The problem is that 5D is the way life works, and it's incomprehensibly complex to our eye. We evolved to just understand 2D plus time for threats like that, okay? We don't know squat about how to interpret 5D. So, I'm the last guy on Earth who ever wanted to do AI, and I feel like AI applied to microscopy has largely been bullshit so far because it's very brittle in the applications. But we're left with no choice but to build minds that can see across vast 5D data and report back the results to us in a way that we can understand. And that's the Cell Observatory. So 6 months ago in the Janelia 40CP AI talk, I introduced what we were trying to do with this Cell Observatory initiative. The problem is that the complexity of the microscopes, and particularly the complexity of the data, is so great that we're making a transition similar to astronomy made at the beginning of the 20th century when telescopes got to be too big to be built by individual astronomers. And instead, the type of imaging we need to do has to happen in some sort of larger group in order to get results. And so we're developing this to specifically start with zebrafish as a model organism to do this. So what are the 4 pieces of the puzzle to put that Cell Observatory together? We need reagents, again, zebrafish, so lots of transgenic and knocked-in fish. We need imaging tools. That's the one thing that we're pretty good at. We need data handling and processing. We're already pretty good at that as well. And then we need the AI tools to build that 5D mind. And that's going to be a bitch. Okay, we'll get into that. So, why the hell don't you like me? Okay, it's going to be... were you at the last year when we were at ASCB and it just all completely crashed then? Yeah. Let's hope this is as bad as it gets. Okay. Anyway, so again, we want to choose zebrafish as a model organism. It's a vertebrate, 70% homologous. Roger would say it's still not human and still not relevant, but it's the best we can do right now. So that's what we're doing. It's amenable to drug perturbations. It's used in drug discovery to some degree, although not by Roger. So I'm going to break down those 4 steps in this pipeline. The first is production of fish. So from simple to difficult, you start either with plasmids and mRNA injection, or you go up to gene-edited fish in the end. And of course, we know I would love to work with C. elegans because nobody loves the 3-month sexual development time of a fish. And trust me, it's very frustrating, but it just means we have this 3-month to 6-month, if we're doing F1s in the end, delay until we get things going. But as long as we got enough things in the pipe, we should be okay. And this is just a small section of the types of things that we have in the pipe right now. Everything in green are things that are in process. The little circles refer to where they are, whether they're transgenic or working towards towards gene edited at some point. This is just the start. Again, because the initiative hasn't been going for that long, we have a reasonable number of transgenics now, but not really much in the way of gene edited, although we're working on it. So let's look at each one of the opportunities there. First, you start with mRNA injections. We do that a lot because, again, thanks to people like Atsushi Miyawaki, there are better fluorescent proteins all the time, and we want to make sure we use the best, so then we have to rechange our fluorescent protein fusions to use them. And so we want to actually see how those work in fish, so we do microinjections of mRNA, image them, and evaluate the brightness and the photostability and so forth of that. That's part of our pipeline. We also worked with Jennifer's lab, and particularly Heejin, who borrowed some tech from the COVID people in terms of changing the mRNA to be able to be packaged at higher density, so you get more of it inside an injection, so you go from like the left to the right there. And thank God we then have 5 or 6 times brighter fish that we can image with that. Here's an example. This is actually with the plasmid, not the mRNA. Why are you not running? I don't know. That's a good question. But he doesn't want to run. But that was a beautiful movie anyway of injection and then mosaic expression after a while with that. So transgenic optimization is the next step after the mRNA. So we're working with particularly strong promoters to get higher expression. We're trying to use just now getting into these UCOEs, which then make the DNA more accessible to optimize transcription as well. And we're working with new landing pad technologies to get for single copy integration in transgenics. One particularly important transgenic fish for us is something we call Skittles. So it's basically like Brainbow for all the cells in the fish, so a stochastic combination of different colors. The purpose of this fish is to be part of creating annotations for AI-based 4D segmentation. We had a first generation of Skittles, which sort of worked, but it wasn't optimized for the FPs and other things. So we're working now on a second generation. We have one founder who laid 3 fish and then decided didn't want to lay anymore. And then we have 3 F1s coming out of those, and there's more being developed at Genelia. We're very, very grateful for the fish facility here and the transgenics facilities here because they are doing a lot of labor as well as us at Berkeley to build our library of fish. CRISPR knock-ins, at this point we only have one. It's an AP2 knock-in to look at clathrin-coated pits. This is some imaging on one of our scopes showing the individual pits that you can see in a very nice neon green. We can do better than that now, but still 3-second intervals for 3 minutes, not too bad. And that's at 1.27 NA. So the microscope that currently is doing the lion's share of the work of taking the many, many terabytes to petabytes of data we need is the Mosaic. This is something we developed several years ago, starting here at Genelia and then at Berkeley, as sort of a Swiss Army knife microscope to be able to do many different modes of operation. But we use it basically 100% of the time in adaptive optical lattice light sheet mode to look in fish. So this is showing development in a fish in the tail region here. And you can see muscle cells and internal cells there in the spine. It uses resolution down about 250 by 300 nanometer. Peak throughput, like I said, 4 terabytes an hour, 2 cameras, simultaneous imaging. And these microscopes now, Gaozhong in our lab runs them and takes care of them. Although they're flexible for other things, basically these are the workhorses of taking data in the thing, and they run all the time in order to take that data. Thanks a lot to Dan here, who makes sure that things get fixed, things go bad, and they do. Next microscope, which is just under construction right now. In fact, it was initially built here at Janelia, but now we're tearing it down and shipping it to Berkeley. Vilat here, who's been at Janelia now for a year or so, has put together, again, the normal lattice light sheet like the Mosaic. It's done upright with 2 objectives and your sample's below. It works fine, but biologists hate it because they don't like having to not have a simple open top design where you can put multi-well plates or things like that, right? And you can't do drug perturbations easily because the volume of the chamber is gigantic and da-da-da-da-da. So Vilat's scope is about 2 things. One is getting even higher resolution and better access to both sides of the fish by having an inverted lattice light sheet design with a little Bruker boat that has an FEP film so you can access both sides of the fish. And also, because we're using 2 1.1 NA objectives, there's some neat tricks that one can do with structured illumination to really be able to push the resolution down very low. Particularly interesting for us for the organelle type studies we'd like to do live. And you can line up multiple embryos inside of one of those wells and go along. But again, everybody who's done light sheet for a while wants to be able to have some kind of open top design, which to a biologist just looks like a normal inverted wide field or confocal microscope that they can run. So most of these are based on this idea by Tony Wilson of relaying an image from a different image volume to another image volume, like this little, if you've ever seen this thing with a frog or a pig that you put inside of this thing and these mirrors relay a 3D image of it on top. The same principle can be used with 3 objectives to basically, you take the sample with your high NA objective, it creates an image, and then you image that image with another pair of microscope objectives to then be able to see it remotely. And because you can tilt that, you can basically then image the light sheet perpendicular to the sample, even though the objective is not perpendicular. So it works. It's a great idea. It's really complex. This is usually called single objective inverted light sheet microscopy, which is something I tend to think is a misnomer because, yes, the biologist only sees 1 objective, but there's 2 high NA objectives that have to be aligned to a hair underneath them that you have to worry about. So, but when it works, it's fine. So we decided to use a different approach to do true single objective inverted light sheet microscopy so we could do multi-well plates. And it's based on something that's been around for a long time, high-low, where instead of bringing your light sheet from above, you bring it through your objective, but by being at the very edge of the pupil, the light sheet comes up at a very highly inclined angle, and so you don't have a ton of out-of-focus light. It's still like a 4-micron thick light sheet, so there's some out-of-focus in order to cover a cellular size field of view, and that works. So one thing that I developed for the startup company I'm involved with is taking that high-low idea and actually scanning the high-low light sheet with a tighter light sheet focus, and at the same time use the light sheet mode of these high-speed cameras to only take the signal in the sweet spot where the light sheet is in tightest focus. And then you're able to strip out all the out-of-focus light, have a tight focus, and you get a much more homogeneous signal, and it's very fast. You can go like 10 milliseconds for a full chip on the camera doing that. So that actually is, I designed that first for the startup company we have for drug discovery. That's Icon. That's their building in Millbrae. The thing on the right is just a movie showing the whole pipeline. They run 30 of these microscopes, 24 hours a day. They take a petabyte a day, so we're not at their rates yet. So the good news is single molecule data is super compressible because you're just looking for positions of spots, so that's not so bad. Yeah, this works reliably at scale. So that's why we thought this would be a good option for the Cell Observatory. So we built one of these OLSs specifically because I had this strange guy, Amir Hay, who wanted to become a postdoc in my lab because he was interested in single molecule stuff. At the time, I was not interested in single molecule stuff at all. He's interested in looking at single molecule level of epigenetics and understanding that better. But I built one of these OLS things for him. And one day, Gokul said, well, why don't we throw one of the fish embryos on it? I said, no, that's going to look like shit, okay? And so we throw it on there, and it looks like this instead. And I go, holy mackerel, okay. So, yeah, it's really easy and really performative. So this is 250 by 250 by 75 microns, 300 time points, 10 seconds to get each one of those volumes. So really, we are starting to get this almost no sparrow shall fall godlike ability to have extremely high resolution over extremely large fields of view for extremely long periods of time with extremely high frame rates with these types of microscopes. That's great, but obviously we're going to be screwed pretty quickly as we go deeper by aberrations in this microscope. So that led us to say, okay, well, let's double down on the OLS architecture and make one that does have adaptive optics like the Mosaic does so that we can go deeper. And so this is the microscope that's just now finally getting to first light. We're actually built two of these guys. Instead of a water objective, we're actually using a silicone objective to better match to the fish. 1.35 NA, so even without any tricks, the resolution will be around 180 by 180 by 500 nanometer resolution. But if we just have our light sheet, instead of being continuous, bounce it off an SLM, we can put a grading pattern on that and do either 3 or 5 phase structured illumination microscopy on that, which would take the resolution down to about 130 by 130 by actually better than 500, more like about 300 if we do a 3-phase sim. The downside is the silicone objective doesn't have a crap load of working distance, but still we can go 300 microns deep, and that'll allow us to take a lot of different cell types inside a fish for the cell observatory. Peak throughput will be even higher. There's some new cameras by Tucson that are even better than the Hamamatsu fusions, so we're likely to use that. We came up with a clever, one of the things is with adaptive optics that usually limits you in how fast you can go, like on the Mosaic, is that the aberration changes as you go through different parts of the fish. And so you have to keep measuring and then correcting for those different areas. In one dimension, that's not bad because we can do the correction, which uses a 2-photon guide star to look at its aberration and then change the shape of a mirror. We can sync that along with our moving of our high-low like light sheet across the field and continuously correct and continuously get a good correction. But we can't do it in 2 directions. And so we're usually limited to maybe 50 to 70 microns in that direction. So what we did is we built this cute little color splitter to use the whole square of the chip, even though we can only do 1 band because of the isoplanatic patch. What we can do is we can split the 4 colors onto 4 bands on the same camera. And so then we can get simultaneously 4-color imaging of different organelles and so forth at the full speed with the full correction. So, oh, too bad. It's so sad to not see the one on the left. That was that little thing going boop, boop, boop. That's Amir and Vilat seeing their very first, or not Vilat, Amir and Neville, the other postdocs, seeing their very first images last Thursday on putting a fish into the Mosaic. And of course, this image is, all these videos are just not working for me. I'm going to get out of this and back and see if that wakes it up. Of course not. There. Well, you can see it this way out of the thing. Okay. So this was their first movie that they were smiling at on the screen there. So they're just parked at one plane in the fish. And you're seeing the blood flow and the erythrocytes. That's the nuclei on the middle channel and the membrane on the lower channel. So at 50 frames a second. And then this is here, mitochondria in a transgenic fish we've developed as part of the pipeline. And this is just a single cell dividing with the mitochondria there. So the microscope still has bunch of problems. We still haven't gotten the AO working right yet, and the sim is still far in the future, but we're getting close on this scope. And I think this is going to be a really awesome scope when we get it right, and it will produce data like you wouldn't believe. All right. So, okay, so we have the first two parts of... Yep. Oh, yeah, if it'll work now. Let's see if we can... There they are.
Can we just increase the contrast on that somehow?
That's me telling them what to do.
Do an auto
But they were very excited anyway, so... even though I'm always telling them what to do. But anyway, so it's an exciting time right now at the ABC, I'll say. So we've been through in that pipeline of doing the cell observatory reagents, images, and then we go from there. So we've been through the reagents part, we've been through the scopes part. I won't go into any real detail about the data handling or the data processing part. Again, we had a paper a year or so ago called about Zhang Tao's awesome predicate 5D pipeline, which allows us to do at very high throughput all the pre-processing. That's what we used for the VIPS paper that was the olfactory bulb. And so we're good at that stuff. We think we're really good at that stuff. So, but now we get to the hard part. Remember, again, we're back to this problem we've got. That's what it is, and there are many, many tasks you could assign to the AI, but clearly the first most important task is to have robust 4D cell segmentation, that we can separate the cells, study them individually, and make sure we can track those cells through time. Okay, so that's the big task, initial task. We benchmarked existing segmentation tools like CellPose and MicroSam and so forth. And while they kind of work at sort of a single time point level to about 70% accuracy of segmentation, if you want to look at anything through time, that means and things are going to go belly up pretty quick. And so we need to have something better. So our belief is that the best AI architecture for trying to understand things in 4 dimensions is you need a model which pays attention to the spatiotemporal relationships in the data. That means a transformer architecture. So it learns the relationships over space and time at all scales, but it requires vast unannotated data for pre-training. Well, guess what? That's the one thing we're really good at, is taking unannotated data. That's easy. It also requires a smaller but still substantial amount of annotated ground truth data. I mentioned the Skittles is one way of trying to help getting those annotated. It's not automatic because you have to go somehow from colors to actual labels, and that's not necessarily trivial. And then also manual annotation. How can we get semi-scalable manual annotation to get enough annotated data to do fine-tuning of the model for the segmentation task? So to get our feet wet, Thayer here, who's in our group and is our ML lead for the Cell Observatory, tested something out by doing adaptive optic correction based on diffraction-limited puncta from clathrin-coated pits inside of the zebrafish, looking at the aberrated images and imputing the correction with a 3D transformer. That particular transformer used a 2-stage architecture of patches that are of 2 different sizes, because that allows you to get a better understanding of, in this case, it was basically because it's in frequency space, basically sort of like the nature of the wavefront aberrations at different scales inside of the microscope. But what's the advantages of that architecture is it converges faster than a single-stage transformer. It's more accurate with smaller models. Thayer did a beautiful ablation study that's part of his paper that was published. I'm really proud of this paper. Again, we didn't do this paper because we want to have an AI way of doing aberration correction. We have a much better way of doing AI or doing aberration correction with our GuideStar. We've been using that for 10 years, and it's highly robust. It measures very large aberrations. It's very fast. It's very non-invasive. The only thing bad about it is it requires a Thai sapphire laser. But other than that, it's good. It's really good. And I don't see any reason to move from it. But this was a good problem to be able to get our feet wet with this type of thing. But the other thing I'm proud about this paper is that I felt like, again, looking at all of the microscopy papers with AI, there's just not enough discussion about where it works, where it breaks, what are the scaling laws, do an ablation study to find out the trade-offs between model size and so forth, and accuracy and inference time and all the rest. And Thayer did all of the hard work in this paper in order to go through that. All right, so how are we going to get these segmented cells? So if we're going to use a transformer architecture, we have pre-training data that we need to take. We need to somehow create annotations, not as much, but still a hell of a lot. And then we have to do some kind of training. All right, so the first order of business is we need to create an industrial type pipeline for how we take care of the data. Okay, so we have data like this, and ultimately this is going to be split up into hypercubes that go into the AI model for training. 5-dimensional hypercubes, X, Y, Z, color, and time. Okay, so we need to develop a sort of both the metadata and the database to be able to have all of that done. So that's all done and well and good, okay? Then we need to do a first round of getting annotations, okay? So the first thing is we start with a paper that came out in March of this year called NN Interactive. It's already built into Napari. They trained it on various medical data and microscopy data for segmentation. It gives us a first cut. It's not great, okay? But then Matt and Danielle in the ABC developed computational tools that are very fast for doing manual curation and checking of that. And you can see this going along. And basically, you put prompts inside of the cell where you think there's a space that's missing, red prompts outside where it's slopping over to the other side. And of course, this movie also decided to just play once and then just die. But anyway, so it turns out this is pretty good. Okay, so Danielle, who's going insane because he's looked at now, what is it? How many volumes has he looked at? 12 volumes each with about 1,000 cells each. So we were somewhere in the neighborhood of 50,000 to 100,000 fully semi-manually annotated cells thanks to this. And so the proofreading time in order to do this is 10 seconds. Now, about 6 months ago, when we were starting the Cell Observatory, we decided to have the tracing team here at Janelia try to segment some cells for us so we could benchmark how long it took. It took them 90 minutes to do a single cell. So it was completely impossible that this would ever scale. So by them developing this tool, plus the NN Interactive to get you the first cut, gives us a really good way to get at least to the 10 to the 4th, 10 to the 5th level of having trustworthy annotations. All right, let me get the next thing. All right, so beyond that, we can get augments to the data by sort of making lemonade out of our lemons. So let's say we have some real membrane data that we have here, okay? We run through this pipeline with the NN Interactive, we get some labels. They may not be perfect, okay? So that if we convolve that with the PSF after it's deconvolved, we have sort of a synthetic data set, okay? A synthetic data set with some little errors in it, okay? Now we can do the PSF, we can change the SNR, so basically we can generate more and more diversity of data, more augments of the data to cover greater things to throw into the model with these synthetic membranes. Now, the synthetic membranes may not exactly reflect reality because of the errors from the NN Interactive, but at the same time, the errors that result in the synthetic membrane data are just a reflection of the labels that came out. So the labels, therefore, are accurate to the inaccurate synthetic data, if you catch my drift, right? So therefore, it's still useful for training purposes in that sense, because we have a one-to-one match between the data and the labels. All right. Again, the purpose of the Skittles was to be able to find another additional approach to be able to generate annotations for segmentation. So in this case, again, we have the stochastic expression. There's big diversity. We can another huge advantage of the Skittles is it will be one of our ground truth ways of being able to track cells through time because of the constants of color. All right, so now we've talked about pre-training data, we've talked about annotation methods, and then you need to get into the training. Okay, so the annotations, okay, all right. So we need to have an idea, we need to figure out, did I skip a page? No, I don't think so. Okay, so where am I in time? Oh, I got plenty of time. Okay, optimizing GPU utilization. So when you start trying to actually train models of any size, you start to get into all of those weedy little things that you don't normally think about, all the devil in the details stuff. And one of them is the sad fact that if you don't do your homework right, you can spend a hell of a lot more time just loading the data into the GPUs of your cluster than the GPUs are actually doing anything themselves. So it was important for us to develop architectures that would allow us to maximize this model flops utilization parameter, or MFU. So as you can see is that, you can see as you build bigger and bigger models, you need a lot more training time. And if you only have a 0.3 utilization, you're going to be, you start getting to be, possibly on the order of factors of 2 to 4 or whatever longer in terms of training times if you're not careful about you doing this right. Okay. So Thayer, along with a fantastic, God, I mean, I hate being at Berkeley, and I hate graduate students in general, but Hugo Hamilton, he's in the what, bioengineering department. Dude's a star. I mean, and so Thayer, I think I would have lost Thayer by now if it weren't for Hugo as his adopted son, basically. And these guys just work great together. But anyway, so the old method of trying to be able to load it up is like this slow, and you can see it takes a long time to load into the, but boom, we get like this 3.7x speed up, just doing all the bullshit hard work, right, in order to optimize this process of loading. It's not sexy, but it makes a big difference. Okay, all right. So after that, one can extrapolate from the existing 2D vision transformers like developed by Google and different sizes of models up to this 22 billion parameter model here, which shows the relationship between the parameters and the time per epoch to train and how long it takes depending on overall training data set sizes. You can see that if we extrapolate from these tiny little 16 by 16 patches that were used, or 128 by 128 patches, up to now 128, or actually probably 256 for us now, you start to see that things on this logarithmic scale start to get ugly, okay, and require more and more data. But you can see that this is the reason why you want to have high utilization, because this can be significant, okay? And so we're up at, what, in the one you just tested, 0.95 utilization, so that's about as good as we're going to get. And then he tested this for one particular experiment and found it lands pretty much right where expected in terms of the curve. For a training set with also it's fairly linear in terms of speed up with more GPUs as we go through it. The default time was 2 hours. Ours is half an hour for 100,000 size, 12 terabytes. And the speed up, again, is the 0.95. So you can learn more about that from there. From all of this, we can guesstimate the needs of the model to do the segmentation task. The numbers are still ugly, but better. For pre-training, you're talking about anywhere from, this is per H100 days. So the more H100s you have, the less ugly it gets. Some of our money comes from CZI. Thayer, after much banging against those people forever, finally has access to their 1,000 node or 1,000 GPU cluster that they have. They just announced as part of their reorg that they're going to up that to 10,000, which made us very happy because right now there's space on it and we use it, okay? So these numbers are not that bad when you think about the resources that we may have available in order to do this. So how much data is enough? That we don't know yet, okay? For a minimum guess of 1 million hypercubes, it would be about half a petabyte. Gokul's best guess is about 10 million hypercubes or 5 petabytes. Nice to have would be 100 million cubes or 54 petabytes. 54 petabytes is a lot of data. Even for us, 54 petabytes is a lot of data, okay? How much data is enough based on that thing? Well, here's a graph up here about how much is needed for each different type of question might ask for pre-training data. We're on membrane and nuclei. That's our bread and butter because we have good reagents for it right now. We take that data all the time. We're already about 40% of the way there, okay? This year, again, we're pretty much limited because we're waiting for all of the transgenics and gene-edited fish to come more on side. But we're of 234 terabytes with one mosaic. And next year, we should have the 2 ISORs, Velott's inverted microscope, the 2 mosaics running, all totaled. When you look at real numbers, not peak numbers in terms of downtime, sleep, breaking hardware, blah, 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 we figure those 5 microscopes should get us around 4 to 5 petabytes a year, okay? So, again, at some point, the pipeline of fish will catch up to us, and then we should be taking data about those rates. So again, then that after we get to the task of being able to do the segmentation, then we start getting into many of the other tasks. Again, basically with the transformer architecture, we're going to build a multimodal model that does many other things. It will segment the organelles, classify the organelles. All the tasks a biologist would be interested would eventually be grist for its mill and be part of this larger training initiative. And so it'll be a 5D vision model. And the thought is, so what do you do with this, right? I mean, we have another problem in addition to in addition to just the size of the data and the complexity of the data as we understand it, which is how do you interact with it once the computer understands it. The best approach right now is an LLM. Okay, so that basically the computer would be the oracle. You ask it questions about what happens when a neutrophil is extravasating through a blood vessel to the nucleus in terms of its shape. I mean, how does the velocity change? You can ask specific questions like that, and if it's in the database or if you have a question that you want, you go to the Cell Observatory, you put in a proposal, your fish will get put into the pipeline, it'll do those kinds of things, and out pops the answer. And then eventually, the goal is by that sort of conversation that you have with the LLM, you get to some results. So that's the thought. So this is the last of the first part of my talk, which is, this is again, the rebel physicist who doesn't understand biology, who thinks biologists are completely full of shit, okay? That they do not understand what's going on, okay? The animation defines life. Life is crazy complicated. You can't look at it with reductionist tools. Almost everything you still read in textbooks comes from molecular biology, structural biology, and biochemistry. They're all about taking the cell apart into pieces and trying to reverse engineer the most complicated matter in the known universe. We understand neutron stars and their interiors better than we understand the interior of cells because the complexity is so many orders of magnitude greater. And so this reductionist approach to biology is never going to get us to an understanding of what's going on. So some of you may have seen the movie Moneyball about how sports analytics revolutionized baseball in the early 20th century. So there's this scene in which the math nerd is telling the Billy Bean, the general manager, that baseball was medieval because they were going based on just sort of gut and thought about who are the right players. So I think this is relevant to our situation, and I said there's an epidemic failure within biology to understand what is really happening, and this leads many people who run granting agencies to misjudge the opportunities and mismanage their budgets. Biological thinking is medieval. They are asking all the wrong questions. That's my hypothesis. So with that, I'll first stop here. Cell Observatory team. If you guys knew me with Harold in your lab or at Janelia, I averaged 3 postdocs when I was here, and that was about all I could handle, okay? That's all I wanted to handle. I never wanted to have a big group. This looks like a big group, but it's not a big group to me because pretty much I'm responsible for those guys on the left. In the middle, you have Gokul and Dave. On the right, you have Thayer and Dan, okay? So they're basically the PIs of those parts of the project. And I have to say, the team is really humming now. It's taken a long time to get us to this point, but they're starting to knock it out of the park on all of these fronts. And all of the leadership just sweats blood for this. But in particular, I can't say two people I want to signal out. First, Thayer. I don't know how the hell we found you. I don't even remember how the hell we found you, okay? But this guy is a star. He's Jan LeCun, all of those guys, I can't hold a candle to this guy, okay? I mean, seriously, he is really at the top of the game in AI stuff. Unfortunately, fucking Janelia won't let me pay him more money than he's worth, but fortunately, he's high enough on Maslow's pyramid that he's willing to sacrifice what he could be making on the other coast to do this fun project that we have here, okay? The other person is Gokul, okay? I pride myself on being one of the hardest working people I know. The only person I knew before a few years ago who ever touched a candle to me for hard work was Harold, okay? Well, Gokul beats us both, even in our best days at Bell Labs. Not only does he beat us both, but A, he has the patience of the Buddha. He never gets angry. He's always just unflappable, and he's a polymath. Everything that I said here in this talk, when I'm talking to microscopy, trust me. When I'm talking transgenics or AI models, I'm skating on thin ice, and I've been drinking from the fire hose for the past 2 days to try to understand this. It's all in Gokul's head. He is a polymath who is expert on all of this. And you talk about deletion test, you could probably kill any one of us and this could still go. You kill Gokul and it's done, okay? It's absolutely done, okay? He's an amazing guy. In fact, if Janelia had any sense, they would be pulling this whole effort here and put Gokul in charge of it as a group leader. Because, man, it is a bitch to try to keep getting funding and keep that force field around the 3rd floor of Barker Hall to keep all the bullshit of Berkeley from infecting us as we try to work, okay? All right, so that's the end of the first part of the talk. Now, in a few minutes, I want to talk about, I'm very excited still about the Cell Observatory Initiative, but I'm going to tell you why I think it might fail too, okay? Not that we won't be able to understand biology better than before. Not that we won't have tools that are far in advance of anything we have now to understand biology. The Cell Observatory Initiative arose as an answer to this talk that I gave here almost 2 years ago now about what was wrong with everything we were doing in microscopy and why we weren't affecting biology hardly at all, okay? And I still believe that, okay? And it comes down to Charlie Munger. I love this man and I hate this man, because once I learned this phrase of his, to me it explains everything in the entire world. Everything in politics, everything in economics, everything in science comes down to that sentence. If you show me the incentives, I'll show you the outcome. In the Confessions talk, I said, all the talk that tool builders give about open access, open source, commercialization to make it useful, they have not moved the needle in microscopy-based discovery, okay? And the problem is because, and I won't go into it again, you can go back, it's on YouTube, you can see that talk, all the arguments, it comes down to the incentives. The incentives are such that all three of those approaches are doomed to fail, okay? But all that being said is, despite all of those incentives, there are a few, and I keep saying in my talks, I've worked with the beautiful thing about Janelia was the visitor program, right? I mean, in the heyday when we're doing Lattice and AO and SIM and all that stuff, we just, week after week, even after the AIC was gone, we brought people in, boom, 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 for a week at a time, take data. Most of that goes nowhere. Some of those people are really dedicated. They dig into that data. They write good papers. This is some of the examples of things that I felt were like hits, okay? We were learning stuff. These papers were really good, solid papers. And guess what? Nobody knows about them. And I think this is true of a lot of good work. The good work is lost in the noise of a lot of shit. And even when you see it, you read it, and then you forget it, and you don't think about it, and it's just gone. Science is so vast that you just can't keep your mind around all of that stuff and what you should keep your mind around. So even if we succeed with the Cell Observatory, and we put everything here on steroids, and I can ask the model to just take data from inside of a fish, of any one of these things, and it will out-pop a paper or anything I want with all the graphs, everything, boom, boom, boom. We could do that. That's a possible future, and still it may make no impact. Because, again, its impact means somehow affecting the humans and how the humans interact and use that information, okay? So, I think there's a bigger problem, okay? And this is me really flying off the handle now. The way science has succeeded since the time of Newton, right? Or earlier, Archimedes, is by taking complex systems and break them down into understandable smaller pieces you can experiment on. Reductionism. It's been super, super effective. We have Newton's 3 laws. We have general relativity. We have all of this, all because we have, the structure of DNA. All of these things are based on this reductionist approach. We don't even understand. We're like fish in the ocean who don't see the water to understand how much this reductionism affects everything in the way we think and go about science. There is one scientific question in which reductionism is the wrong answer, and that's to understand living matter, because you can't reduce it to its parts. You have to understand it whole, okay? And so even if we have all of this stuff, if all we have is the imaging side of it, it's not enough. Some mind has to exist which can understand the totality of the information, the imaging information, all the orthogonal information that comes out of those reductionist approaches, and put them all together. So it's probably not enough just to have a multimodal model that looks on imaging. It has to be a multimodal model that understands biochemistry, molecular biology, structural biology, and can tie all of that together, okay? That's crazy, I know. I'm not the only crazy person who has that thought. A year ago, I went, when I was trying to get money for Cell Observatory, to a thing in Napa where there was a lot of people, including this Sam Rodriguez guy who has this sort of semi-official startup called Future House. He gave this talk, and I almost laughed him off the stage thinking how stupid the idea was. Their idea was throw every scientific paper ever written into an LLM and train an LLM on it and have it become sort of this oracle of science. Okay, all right. Well, first of all, You may remember, like in 2015, Nature did a self-survey of their readers and said, how much of the scientific literature in your field do you think is erroneous? And the answer came back about 50%. And then the second question was, how much of the stuff you've published is erroneous? The answer was about 30%. Okay, so I figure, okay, they put this thing together, and it's just going to be nothing but a massive hallucination. Okay, but still, conceptually, obviously there needs to be some kind of vetting. But conceptually, I think the only way that we'll get past this reductionism that is killing the understanding of life is by pulling every piece of data we have together from all sources and then doing the opposite of reductionism, having models to try to put that together and then in some way interpret to us. It's still science fiction to me too. I don't know. But I just keep thinking that the approach we're on of all this reductionism is really the wrong way to understand biology. And I'll leave it at that. Thank you.
Wonderful. Let's open this talk to discussion.
Or debate.
Let's get up here, guys.
I'm intimidating.
Okay.
Again. All right.
Jerry, you're the perfect person.
Jerry,
Okay.
So as a unapologetic
reductionist. I was looking at you several times as
this discussion.
Yes.
No, I mean, I understand. I'm not arguing what you're saying, but even in your talk, you talk about this little thing over there where you have ancillary biological data.
Yes.
You need that. You need the crystal structures. You can't.
I just said that.
I know. So
Yes.
that's reductionism. So you shouldn't say that. No, you implied no grants. Nobody should be doing reductionist work anymore.
I did not say that, and I did not imply that.
Well, fine, good. No, we clarified that for me. Thank
So-
you. Thank you for clarifying that because.
But I'm saying that the overall emphasis, by far, of biology is
Okay,
reductionist.
we dealt with that point.
Yes. Okay.
So,
Good.
Understanding.
Yes.
So, as a reductionist, I have trouble saying the level you're looking at this of pictures of cells doing shit,
Right.
to use your technical term,
Yes.
it cannot lead to understanding that would be satisfying to me.
Yes. Well, that's TBD. I think
We'll be both dead, so it's okay.
What's that?
We'll both be dead.
We'll both be dead. That's certainly true. Yes.
Yeah.
But on the time scale, this is. But I disagree that it won't be as informative as any reductionist approach you have. In fact, it's just reductionism on a different level, right? If I'm looking at organelle contacts, I can learn quite a bit about, particularly if I tie it into the biochemistry, about, as Jennifer does, what reactions happen and what functions those reactions
But
have
where
at
do
that
you get
level.
the information what I'm saying is, where do you get the information to tie it into the
That's what I'm saying.
biochemistry?
This is where it has to be multimodal and use all the information. That the imaging itself is a type of reductionism, right? But it's
Right.
reductionism with some global context, right? And so laying the other types of reductionism, which are more divorced from the cellular dynamics and structures, I think is beneficial to be able to further understand
All
the
right, so we're
reductionism
basically
you
gonna end
have.
up sort of pseudo-agreeing. But
Yes.
I do want to say that I think a reduction in the complexity can come from understanding the complexes in the cell. Like, you don't want to talk about individual ribosomal protein. You want
No.
to talk about a ribosome because we accept that's a functional
Right.
unit, and we're all,
Yes.
even if it came from very reductionist work, you're willing
Right.
to accept a
Yes.
ribosome. You don't need
Yes.
to look at 50 different proteins.
Right.
So there are different orders like that, and we're a long way from knowing about what most of the individual complexes of proteins in the cell are. And if you knew that, you'd have fewer moving parts, and you might have more of a chance of getting to where you want to go.
Not quite sure I understand that last part, but yes. Basically, you want to be able to find, I guess,
I don't want to deal with
Other
10,000
dimensional
proteins. I
spaces
want to
where-
deal with
where you can
4,000
understand things simpler.
molecular machines rather than
Yes.
10,000 individual proteins.
yes.
Right? So you're already doing that because you're talking about organelles and nucleus and DNA. And
Right, sure,
So you're
exactly.
doing that to some extent.
Like I said, there's emergence on all these levels, and we got to understand the emergence on all the levels.
Okay,
Right.
we can agree.
Okay, fine.
Okay, who's next?
Misha?
Misha, good.
Further. I have a question about the other side. Sounds, I agree with your vision of multimodal data ingestion into a large artificial mind. That's correct summary.
It's easy to say, isn't it? Not easy to do.
Yeah. So on the other side, but then there's sort of this like human understanding piece, which
Right.
is not so satisfying, whatever that means. But are you imagining that? I want to draw an analogy to interacting with a person. You'll never fully understand another person.
Sure.
But you can ask them lots of questions and gain an intuition, and being able to build an intuition while asking questions and probing where you want to, you can start.
Yeah, this is the hope, right?
So that is your vision for the
Oh, yeah,
other
yeah.
side, right?
That you have a conversation with the LLM in which you try to learn from the LLM exactly what you want to know to the rate at which you can absorb this information. And the LLM, there's also the other side of the thing, which is what do you want to do if you want to apply what you've learned, right? And the LLM could be very helpful in that, right? I mean, it could see relationships with, I tied this together from the imaging with this from this particular drug candidate that failed trials, and I think if you did this to the structure, it will do this instead, right? I mean, that stuff, again, science fiction, but there's a potential path to having utility in that sense as well as just explaining and discussing with the model, yes. But I do also think that, again, maybe to go back to this reductionism of science, not just reductionism in the sense of breaking the cell down into parts, but the reductionism of how scientists work. Okay, I mean, I'll have a neuroscientist here. Oh, they don't care about your fucking flies, right? I mean, it's too artificial. I'm only going to understand rodents and beyond, right? I mean, this kind of thinking. Or I study, Tor, or I study Tall 2, or I study this or that. It gets to be so like this, and scientists are in such tiny little niches of stuff that it just feels like it's inefficient. It's inefficient to be so focused on one particular type of thing. And I think models, if they were intelligent enough, big enough, or whatever, could lead people to see connections between things that currently we've all made these moats. We go to conferences in which we talk about one thing and one thing and one thing and one thing. There's very little effort at kind of integration of things. And potentially in the future, models would help to lead towards that kind of integration. Yeah. Smell. Yeah.
Yeah. Very interesting thoughts. And what I'm thinking is that the non-reductionist idea is amazing, and I think that's how biologists should see it. But by taking that into an AI or LLM, I feel you're actually reducing it again.
Yeah,
So
I mean,
it
comes up with a latent representation of that data, right?
It's going to use the knowledge that is out there based on reductionist concepts.
It can. I mean, it depends on how you build the model, but I agree that multimodally, ultimately, we would like to use all the information that we trust.
Yeah, I'm just thinking that I still trust human minds for a while.
Yeah.
And I think the data that you're acquiring is going to be seen for the first time. Mm-hmm. And not seeing it at all and feeding it into the AI because of the storage capacity and all that is maybe a mistake. I think we should still look at it.
And believe me, all of our data is on the site. You can download just like the other things. But I asked, for example, like CellMap. There's just not a lot of hits. What you'll find is all of these open source databases people have just don't get a lot of hits. They're not used. And so that's another problem, right? And so it has to be somehow in a form that, again, Charlie's talking in my head, right? What is the incentive for people to look at other people's data? I don't know. You have to be somewhere a little higher on Maslow's hierarchy to care about the other guy's data, not your own, right?
Yeah, I'm not
John.
sure I'm going to say this. So I think our tools have advanced so fast, and we as humans have not advanced that
Right.
fast. So we cannot absorb all this information. And you're right, all this stuff that's out there, nobody looks at, right? The great data resources, but if...
I can't think of a single paper in my career where I've worked with a biologist, had something, and no, one example. There's one example that's been a hit, and that was the experiment with TEAJ to look at the transcription factors, okay? And seeing the speed of the transcription factors and that they weren't binding like the biochemical model suggested, where they had to form an initiation complex. That has had a lasting impact. But I think that's the only experiment in any biology we've ever uncovered that has had any kind of lasting impact on the way we think about biology.
I just have to push back a little bit.
Good.
Okay.
You'd be the perfect
So
person
let's
to
talk
push
about
back.
CRISPR.
Yeah.
CRISPR came from incredible reductionism,
Yeah.
where you're looking at bacteriophage.
Sure.
And, people who were doing it were focused on yogurt products, et cetera. Look what CRISPR has done, and it's only because of incredible reductionism. Look at the way that you're even manipulating
Right.
your fish.
Of course.
We
It's because
need,
of those
It's
tools.
all, mRNA
Yeah.
technology,
Of course.
et cetera.
Yeah.
All
It all
done
comes from reductionism. Absolutely.
Exactly.
Yes.
And I do agree with you that we're at the stage now where we can ask different questions at a holistic level. And these reductionist approaches are in some way flailing because they have not been traditionally directed at these big holistic questions. And so we need a different approach, which I totally buy into what you're doing. What my problem is with what you're doing, and I think it's going to be an issue that you should start thinking about right now, is you start, just as you do in reductionist science, you set up a hypothesis, you have you propose what you think might be driving the self-organization in the system. And right now, all the reagents that you're putting into that system, mitochondria, nuclear staining, all these organelles, we still do not know at the reductionist level how these organelles are communicating with each other. We also don't have a clue at how metabolism, which in my view is the self-organization of this whole system. You have no probes for any kind of metabolic.
Right. Absolutely.
And so it won't go anywhere until you start integrating all of this other stuff. But that requires the reductionist thinkers. The metabolic pathway is all reductionism, big time. And so the two need to bridge each other. So I'm all on board.
But even metabolic pathways are, from that reductionism, are
we need
fraudulent in some ways, right?
Well,
they're far more complicated than the
need modeling,
pictures
AI
they
modeling
put.
for sure.
You'll get one enzyme that will catalyze 12 different things. This is not part of those models right now, right?
Well, they could be if those models are simulated in a bigger scale. And I think that's where what you're doing could be
so I'll disagree on two fronts. About using simulation as the way as opposed to observation. And the other is I believe in hypothesis-generated science when you have enough information to make a reasonable hypothesis. I don't think we're there at that point. I think we are still in the Keplerian era of looking and seeing the planets and seeing the epicycles and things like that. We're not at the point where we can say, well, I think there's an inverse square law that's behind that, right? We're not at that point.
So when are we going to get at that state?
Not for a long time, right?
I mean, you're basically Brahe collecting data right now. And so you need the reductionist scientists. You need the people like, Kepler to start
my point
bringing
is
that together.
My point is not that let's take structural biology, molecular biology, and biochemistry and kick them to the curb and forget about them. That's not what I'm saying. I'm saying that has been largely the only game in town. Okay? The connectome is just structural biology writ large, right? So that's that's fine, but again, it's not going to explain a system of the incredible complexity that is the cell. And I'm totally also in agreement with you is, as far as we can get with this, our tools to see it are still incredibly limited because we don't see metabolites, you're right. We don't see, many, many other things inside it. We see fluorescence 3 or 4 at a time when there's 20,000 of them, right? We are lacking in many, many tools.
Yeah.
I do think, however, though, that our abilities to be able to see life as it is, and I contend that life as it is life in the organism in which it evolved, okay? We've done almost none of studies of life in the organism in which it's evolved at the subcellular level. We're the only guys who know how to do it, right? I think that there will be insights that come from just observing that and, again, tying it to the reductionist approaches. That's my thesis. Not that I hate reduction in general. I would say the success of reductionism has led biologists and scientists in general to all be reductionists when they need to be more generalists in many of their thinking.
Yeah. I think I completely agree with it. I think it's a terrific thesis, especially now that we have microscopes and the ability to do this kind of large-scale screening. We'll just end with, Mung, did you want to make one last point, and then we'll wrap up?
I like the holistic view, but I'm curious to hear your thought about information redundancy in a very complex system. So it's really we need to measure everything we can to understand this complex system. I think we already know there are a lot of information redundancy here because some RNA levels things already show in the maybe organelle or the morphological levels. So I guess I'm curious to hear your thought that do we really need to measure everything, or actually if we can understand how much information are redundant in this complex system, can we reduce our search space?
If you have priors of redundancy, then great. That would certainly help. I don't know what priors generally we have. And the other thing is my experience with playing with 100-plus biologists over the years is everybody has a different thing that he thinks isn't worth reducing and is worth studying, right? So, if we get to general principles that allow for reductionism of the approach of, it's not this, it's all you need to know is inverse square, and then you can figure it all out, that's great. There's not a lot of, again, from reductionism, we've had some hits in that, but in terms of a dynamic sense, not really. Yeah.
Okay, well, let's give Eric an incredible thank you. Really amazing work and lots of thoughtful thinking.